Okay, so welcome to the second half of a semester. That's just flying by. And all three of you who are here. So, I guess everybody else is set to enjoy the holiday, hopefully. Um, okay, now, um, yeah, it's interesting. Tomorrow we're celebrating Independence Day. While I'm flying to the country we won independence from. Go figure. Um, so I have something a little different in store. It's meant to pave the way for some sort of default project if you don't come up with one of your own. So if I want to do something that was more interesting, a nice visual application. So we're looking at image processing. Um, and in particular, image processing based on solving nonlinear PDEs, nonlinear diffusion specifically. So what I'm going to do is discuss one a very well-known equation in particular that's used for this purpose, and that in my own work with my colleague Patrick Gudotti from University of California, Irvine, we made some improvements to, and go over some of the building blocks used for solving this kind of PDE numerically. That would also be useful for solving many others. Okay, so I may not fill the whole time. Well, I have to get going down to New Orleans soon, so I don't want to end class early anyway, and plus there are only three of you here. So here is the PDE. And this is taken from right now I'm looking at in my numerical analysis textbook the exercises in chapter 14. Now now it says here on the screen exercise 11. In the version of the book that I sent to you, it's exercise 10. Because I've added an exercise before that about solving variable coefficient PDE using finite differences. This is one that's worth talking about too. So I will send you, after looking at this one more time to try to make sure there are no mistakes, send an update PDF so that you have both exercises 10 and 11. Because in a chapter it's discussed how to solve a PDE like this one when the coefficients are constant, in which case you have like ut is equal to a constant times uxx. That's all worked out in the text, but you have to do things a little differently for variable coefficient case, and that's what this new exercise 10 is about. Okay, now, but first let's talk about the PDE itself. So this is a Perona-Malik equation. It's relatively new, so it's not even 30 years old. And in fact, in the original paper, it was first used not so much as a PDE, but it is already discretized form. So this is really a numerical procedure first. But then if you take the limit as delta t, delta x goes 0, then of course the PDE pops out of it, and this is what you get. So this is similar to a variable coefficient heat equation in that you have the UdT is equal to the divergence of some coefficient times the gradient. So it's almost the same form as what we have up here. Like if alpha of x was constant, you'd have a spatial derivative of coefficient times spatial derivative, and then summed over x and y. So in fact, if you expand this out by product rule, you'd have d dx of this times du dx plus d dy times this times du dy. But what's different from the equation up above is here the coefficient depends on u, or specifically ux and uy. So that's what makes it nonlinear. So why would an equation like this, that's meant to simulate something along the line of heat diffusion, where you have whatever heat sources altering the temperature in the spatial domain over time, and spreading out to bring the space to an ambient temperature. This is what happens physically. So why would that help with image processing? So I'm going to attempt to show you. Okay. Well, I'll just type into my usual Python editor in the comments here. All right, so Perona-Malik equation. All right, now I'm going to take a one-dimensional form of it just for simplicity. Stop it. Okay, du dt is equal to d dx of 1 over 1 plus k squared ux squared times ux. Okay, so this is a Perona-Malik equation scaled down to one dimension. So in other words, we're assuming that du dy is equal to 0. All right, because then in the simplified form, I can explain to you why Perona-Malik equation solutions behave the way they do, and why this is a good idea for image processing. So I'm going to carry out some calculus here, and I've done this before, but not in a few years, so we'll see how it goes. Okay, so because here we have product rule, d dx of this coefficient times this du dx. So if we actually carry this out, so then I have the coefficient times uxx plus the derivative of a coefficient times ux. So that's going to be minus 1 plus k squared ux squared to the minus 2 times the derivative of what's inside, which is equal to, you need more room here. Nope, even more. Okay. Times the derivative of this inside, so that's going to be 2k squared uxx. Again, my chain rule again. And all of this is times this, ux. Okay. So, kind of a mess here. But now what I want to do is, I want to express this in terms of something times uxx. I want to see what the actual coefficient of uxx is after simplifying as much as possible. So, to do that, what I'm going to do now is, okay, I'm going to rewrite this as 1 plus k squared ux squared to the minus 1. Okay. And now what I'm going to do is I'm going to factor out of all of this mess a 1 plus k squared ux squared to the minus 2. Because that's obviously positive, so it's not going to affect the sign of things. It's a sign of a coefficient I care about. And notice, every term here has a uxx in it. So I'm going to factor it out on the right. And now we'll see what's left inside. So then I have 1 plus k squared ux squared to the first power minus 2, and then this part here, already factored it out, so it's not here anymore. Okay, minus 2 k squared ux squared. Okay. Let's see, did I miss anything? No. Okay. Oh, okay, yeah, that's plus. All right. Okay, it's like, at least it's not a consequential mistake, but yeah. Okay. All right, and now I can simplify here. I have 1 plus k squared ux squared minus 2 kx squared ux squared. I can combine those last terms, or like terms, and what you get is 1 minus 1 times that. Okay, so what that means is um, this coefficient of uxx is not necessarily positive. Um, it all depends on how large this term is. So what we have is if k squared ux squared is, which is going to be positive, of course, if it's less than 1, that's regular or forward diffusion because the coefficient is positive. Um, so, um, so that means we have smoothing. So if we have ux not changing very much, very small changes, for example, that would be indicative of noise, very small changes in pixel values. So the idea is u of xyt is a pixel value at location xy time t. The pixel values being like for a grayscale image, 0 being black, 255 being white, and all the values in between. So if you have noise in your image, you have slight variations in pixel value, but still variations that you can see indicating fuzziness in the image. But because there's small changes, du dx is pretty small. So if it's deemed small, then solving a heat equation of a positive coefficient, as usual, will cause smoothing to remove the noise. Okay. Now, otherwise, we have backward diffusion because this coefficient goes negative. That's going to happen when ux is relatively large. In other words, there's a sharp change in the image indicative of an edge. We don't want to smooth edges. That would cause blurring. So we have sharpening with the opposite effect. So Perona-Malik was contrived to perform both. So it does. So near edges, it sharpens, and then away from edges, it smooths. So now you still have to set the right value of k to determine, well, what classifies an edge. How large does ux need to be for it to be go into sharpening mode rather than smoothing mode. And there's a lot of active research on coming up with different ways of detecting edges to cause the coefficient to go positive or negative at the right the right portions of the image. So this is actually works surprisingly well, even though the equation itself, the PDE, is famously ill-posed because of the coefficient going negative. The backwards heat equation is one of the best-known examples of an ill-posed problem because you can get exponential growth in your solution. The solution does not depend continuously on the data. That's a big problem. So that has made theoretical analysis of this PDE very difficult because a lot of the things that you count on from PDEs about existence, uniqueness, and behavior of solutions doesn't apply. So my work in this area involves certain variations on Perona-Malik to try to get around the ill-posedness. Also, this is pretty effective, but it has its issues too. It can lead to a phenomenon called staircasing, where you have it makes different portions of the image very flat. So then when you have a change of color from one flat region to another, it looks like, in one dimension, it looks like a staircase. And what can happen is the image gets a cartoonish look to it. Because it doesn't, in other words, you don't have like variations of color like ramping up. So that's one problem. And so some work that I was involved in meant to get around that. Okay. But this was a very good start. So this is basically like the starting point for PDE-based image processing, and there's been so many variations of different kinds to improve on it. Okay. So what I've done here, and so I'm not going to give away the code, but I will discuss certain pieces of it. I want to show this to you in action. Okay. All right. So from my file, Perona-Malik.py, I'm going to import a single function called denoise. So I've made denoise, my function denoise, accept a single parameter k, the value of the coefficient k that I use in here. And I'm going to choose one that's, even though it seems small, it's actually relatively large for my purposes. And I'm going to choose a few different parameter values and show you the effects. Okay. All right. This is actually Haley. So, hi, Haley. And I found it easier to take a portion of an image. Like this image file wasn't very large to begin with. It's like 500 something by 500 something, and there's like a 150 something roughly each dimension. Because if I took the original image and just scaled it down, then it'd be lower resolution. I want to keep it high resolution. Also, using the original image its original size leads to a very large matrix. We're talking like 25,000 by 25,000. And that just slows the numerics down. So working with small image files at high resolution seems to be best, at least for experimentation. Now, what I have here, okay, this is the original, but what I did was I had a color image, and I'll show you how to do this a little later. An image file, this is a JPEG image, is represented as basically three matrices. So the size of each matrix corresponds to the width and height of the image, and then the three of them correspond to the RGB channels. So each channel is a grayscale image on its own, with pixel values between 0 and 255, 0 for black, 255 for white. So all I did here was I just took the first channel corresponding to red. But if you take each channel and you look at them as the grayscale images, for a typical image like this one, they tend to look the same, roughly. So this is a channel. So this is the original. And then I added some random noise with a Gaussian distribution. And so I'm still not really sure why it got this much, appeared to be this much darker, and it might be an artifact of how this image is being shown. But we see that it's gotten pretty fuzzy. And so we see these, I wish I could make this bigger, but actually what I might try doing afterwards is if I run this as a script at the prompt, it might show up bigger. But there's small variations in color here that indicate noise. So then what I do is actually run my numerical method, and I'm going to solve this using time stepping. It's actually I'm using backward Euler, and I'm just going to take 10 time steps. So here's the result of a first time step, and I'm just going to keep going. It's pretty quick because it's not a very large image. Okay, now, so what I've shown here, I'm going to confirm which plot is which. Okay, this is the noisy image. This is the final result after taking the 10 time steps. And then this is the original image again. And based on the parameter value that I've chosen, what you can see here is it's still pretty fuzzy. It didn't really do anything. And after I um, show you this again with different parameter values, I'll explain why. Okay, so let's try something a lot smaller, 0.005. Okay, so that's the first time step. Okay, what's happening now is the fuzz is gone, but it's gone too far. Now it's blurring, like a lot of detail in the eye. Oh, yeah, the eyebrows practically gone. So Haley's becoming a ghost. So, um, yeah. Oh wow, that. Yeah, Haley has gone full Casper. So, um, I don't even remember what's happening. Well, I might not try this particular value, but I tried something nice and small. So let's get this over with. Okay, yeah. So not good. So let's try something intermediate. Okay, so 0.05. Okay, so okay. And here we have an intermediate result. It's noticeably better. Okay, so yeah, original, processed, and noise. So now it's obviously not ideal. Some detail was lost, but it's gotten rid of a fuzziness pretty well. So here we have a Goldilocks problem, a Goldilocks situation here where first was not enough, second time was too much, and then here it's closer to just right. And if I messed with K even more, I could probably find an optimal value in this case. That sort of thing would vary from image to image. So what actually happened here is as to why we got this different behavior and the effect of K. So let's suppose that K is relatively large. Well, that's in the denominator, so that makes the diffusion coefficient relatively small. So that would mean that du dt is roughly 0. So not much change of any kind is going to happen. On the other hand, let's suppose that K is very small. Then the diffusion, because in the denominator, the diffusion coefficient is relatively large, so that's going and positive. So that's going to be a lot of forward diffusion all over the place. It's going to be smoothing. If I had continued that process from before of a ghost eyes here, if I continue this, eventually even these would have gone away. So, so now we see the effect of choosing K. We got to choose it just right so that we don't get too much blurring, but we actually get some smoothing as well. All right. So, any questions about what just happened to these images? Okay. So, the goal is for you all to be able to code up something like this, or even code up this, and maybe try some different methods. I have some papers where we have other PDEs, different diffusion coefficients and such. I can point you to those, and you can try experimenting with those. Because once you have the code to solve this numerically, then you can adapt that numerical method to variations on this PDE. Because a lot of the building blocks for such a numerical method would be the same. Because you need to be able to compute these first partial derivatives using finite differences, for instance. Be able to handle computing gradients and also the divergence of whatever function. So as long as you can handle partial derivatives with respect to x and y, then you just choose a time-stepping method such as backward Euler or Crank-Nicholson, and you're good to go. Now, in my actual research on this, I work with spectral methods involving, so that would involve a fast Fourier transform. So that would be an additional layer of complexity, but also one that's worth looking at. Okay, so, right. Okay. So the idea is, okay, actually, let's save this. Okay. So, um, so our PDE, if we express it in this form, du dt is equal to some nonlinear differential operator applied to u that involves both coefficient and computing these partial derivatives to a system of ODEs. So that'd be like u prime of t is equal to a of ut, where a again is it's no before with linear PDEs becoming systems of linear ODEs, we had like y prime equals ay, where a is this matrix vector multiplication. But now it's not that anymore. It's a and instead it's like a function of u that could use u in various places. Now, in terms of finite difference operators, okay, so we have u prime is equal to, so if I keep in mind the Perona-Malik equation, we have differentiation out front of this expression as the coefficient times a first partial derivative. So we have partial derivative with respect to x applied to times g of u times partial derivative with respect to x again times u plus partial derivative with respect to y, same coefficient, g of u, partial differentiation with respect to y again, times u. So here's where the nonlinearity is the fact that we have u out here. Here we have a matrix multiplying u, and in the middle of this matrix we have this matrix that also depends on u. So that's what makes the whole thing nonlinear. So dx is a partial differentiation with respect to x, and similar for dy. And all of these I'm about to describe here are matrices that we need to implement all this. And then G of u is a diagonal matrix with values of the coefficient at the various grid points that make up your image, and diagonal matrix. So this is how you handle multiplying by a coefficient. Because all you're doing is you're taking some vector, you're multiplying that has represent a function at grid points, and then you so then what happens is you evaluate your coefficient at those grid points, and then that gives you so if you're representing functions by vectors, no matter how many dimensions they're in, 2 dimensions, 3 dimensions, 1 dimension, whatever, you represent functions by vectors, and then so here the diagonal of this is a vector that has a values of a coefficient at all the grid points, and so then you're just multiplying vectors together component-wise, and that's similar to that's equivalent to multiplying a vector by a diagonal matrix that just scales each entry of a vector by the appropriate value. Okay, so once we have all of these pieces, then we can define this function of u that's our time derivative. So then for time stepping, in this code, I'm just using backward Euler. So n minus a of u n plus 1 times dt. But the way I'm doing this is because I only care about getting first order accuracy, what I can do is cheat. I can say un plus 1 is equal to un. Oh, whoops, that's a plus. Okay. Plus dt times, if I expand this out, I could do this. Dx g of un dy plus dx, sorry, that's dx again, dy g of un dy, all applied to un plus 1. So by evaluating a coefficient at solution for a previous time step, if I wanted true backward Euler, I'd have gn plus 1 in here. But what I'm doing here is cheating and it's using un. So this is a linearization of this system of entirely nonlinear ODEs. So what I can do now is I can do this. Identity minus dt times all of this. Well, I'll just abbreviate it A. A is equal to all this. Okay. So now I can just solve a system of equations every time step. Now, because I'm linearizing, that immediately knocks me down to first order accuracy in time. But backward Euler is a first order accurate method anyway, so that's okay. So in my first paper on image processing, that's just what we settled for. And then in the second paper, I used the first order KSS method with the same linearization. If you want to really keep high order accuracy, you really want to use a higher order time stepping method, then you're using, like for instance, methods of Runge-Kutta type, and most sophisticated ones are, for instance, EPI methods that I use in my own research. So it's a lot trickier in that case, but those things have been worked out to yield high order accuracy in time. But that involves several applications of this operator to certain vectors to match Taylor series terms up and so forth. It's kind of a mess. So we'll keep things simple for now. Okay. So a couple things that need to be dealt with. One is, this is a large matrix. So if you have a m by n image, then the matrix is going to be mn times mn. So even a relatively small image, 100 by 100, let's say, then your matrix is going to be 10,000 by 10,000. Now it's going to be very sparse because we're using finite differences, so that helps. But that's a sort of system that it's generally a good idea to use an iterative method for. Um, and we've talked about certain iterative methods, like some that play a role in the first homework, um, like Jacobi or Gauss-Seidel. Um, now, this matrix is, in this case, is symmetric positive definite. Okay. So you could use conjugate gradient. But my first attempt at coding this actually was not conjugate gradient. I used Lanczos iteration, which is actually equivalent but not as efficient as conjugate gradient because it's solving a larger system of equations every iteration. But and what I found was it wasn't very effective because this is the ill-conditioned matrix, so conjugate gradient would be slowed down by that. It's sort of problem that you ought to use preconditioning for. Now, an alternative, which is what this code used, that seemed to be, well, actually, I had a number of bugs in my code, so it's hard to say which method was better than the others. But this method here is working well. It allows me to, so I can't honestly say whether this is better than conjugate gradient for this case, because I haven't properly tried conjugate gradient yet, or Lanczos, because of other bugs that I discovered and had to fix. So that's something worthwhile checking out. But it's still worthwhile looking at an alternative method because it exposes you to other tools in NumPy and SciPy that can come in handy. So the method of choice that this code is currently using is called minres. So it's a minimum residual method. So the goal is to find a solution in a certain subspace so that the size of a residual the residual of ax equals b is r, which is defined to be b minus ax. So of course we want that to be small. So the minimum residual method minimizes r over all possible solutions x that are confined to a particular subspace, a Krylov subspace that keeps growing as the iteration proceeds. And this is, minres is for a symmetric matrix. If a matrix is not symmetric, then there's GMRes. That's one of the best known iterative methods. It's a generalized minimum residual method. And that's quite effective for unsymmetric systems. And the way we achieve a minimum residual is to solve a full rank least squares problem. We haven't talked about least squares yet. That's discussed in chapter 4 of the textbook. So that's something I'll be covering today. How do we use NumPy to solve least squares problems? Because we've seen it for solving ax equals b in a case where A is a square invertible matrix, but here we have a slightly overdetermined system. Okay. All right. Actually, I'm going to take my first break at this point, because... All right. Okay. So my goal here during the time that we have left is to go over some of these essential ingredients in solving this kind of equation. Number one, constructing the partial differentiation operators for dx and dy, using either forward difference, center difference, or backward difference. All three are useful. And then minres, and in particular solving a least squares problem that's an ingredient in minres. Now, I'm not sure how this will go time-wise. So since we're not going to meet again in class for 2 weeks, not until July 17th when I'm back from London, my plan is to still record some things, especially if there's anything I don't get to today. and post them. I'm not sure if it'll happen for all free class sessions, but if something is posted, I will let you know. So something to watch for. Okay, now, all right. Actually, let's talk about least squares. So the idea is ax equals b, a is m by n, m greater than or equal to n. Really the case where m is strictly greater than n. I'll just focus on that. Where the rank of a is equal to the number of columns. So in this case, the system is overdetermined, because if m equals n, then we're back to the usual case where we do like Gaussian elimination. So what you can do in that case is so really generally unless b happens to be in the range of a, x equals b is not solvable exactly. So you minimize the norm of residual, the two norm of residual instead. And two general approaches to handling this is normal equations. You solve A transpose AX is equal to A transpose B, because now A transpose A is an n by n symmetric positive definite matrix. So for instance, you can use a Cholesky factorization to solve it. So you're back to the square n by n invertible case. The other, which is more numerically stable, is QR factorization. So you solve, so you have A equals QR, and you solve Rx is equal to Q transpose B, where Q is the columns of A orthonormalized, and then R is n by n, and upper triangular. So you can solve this by back substitution. Both algorithms are order n cubed operations. Well, actually, okay. Well, for instance, here, doing this matrix vector matrix multiplication would be order m n squared. So it's still a cubic algorithm essentially, and what we have here is n columns, but they're both all of length m. So the expense is not very different between them. And there's a few approaches to doing QR factorization, like Householder reflections, Gibbons rotations, or Graham-Schmidt, which is the worst. Those of you who haven't taken Math 610, you'll learn all about them there. Okay. So what I want to do here is show how you would do this in Python. So I'm not really going to go ahead and like implement one of these from the ground up in Python, but use standard functionality in Python, like in NumPy or SciPy, to solve it, just like we've seen how to do with ax equals b. And I'm going to do a simple case that where we can do things visually. So all right. So suppose we're given a certain number of points in the plane that are scattered about, and I'm going to generate 10 10 such points. Okay. And for convenience, I'm going to make this an actual matrix that's really a column vector. I can do the same with y, my y values, although it's not required. Okay. And if I were to, okay, I need to import a plotting package. So if I do, for instance, plot x, y with red circles. Oh, whoops. I was going to mess up something. plt.plot. Okay, and there's my points. Okay, so what I want to do is find the line y equals mx plus b that best fits the points in least squares sense. And what that amounts to is I want to minimize this sum over the 10 points of yi minus m times xi plus b. So these minimize some of these deviations. Okay, so this least squares problem, AC is equal to y, where y, vector y, is just the y values. C is a 2 vector that has the coefficients b and m in this order. You'll see in a second why it's this order. I really could have picked either one. The constant coefficient and then the linear term coefficient. So the y-intercept and then the slope. And then the A is 2 columns, E and X. X is the X values, and then E is a vector of all ones. So what I'm saying is, I'm evaluating the functions 1 and x at the x values. I'm saying find a linear combination of 1 and x that approximates the y values as closely as possible in this sense of minimizing the sum of squares. And that's why it's called least squares, because we're minimizing a sum of squares. So because I have a constant function first and an x second, then I have the coefficients first and second, the constant term coefficient and the linear term coefficient. I could have swapped these as long as I swapped these as well. So if you're trying to, in general, you're trying to find a linear combination of specified functions that best matches some given data in a least square sense, this is a problem that you solve. So each column of a matrix is one of those functions evaluated at all the x's. So I wanted if I want a higher degree polynomial, like a quadratic, I'd have 1s, then x's, and then the third column would be all of the x's squared. So this generalizes pretty naturally. Discussion in my textbook, we're actually working on an example like this, and also higher degree. Chapter, actually it's section 8.1 in my textbook. Least squares is discussed in depth in a numerical linear algebra sense in chapter 4, like all these methods that I talked about over here. But in terms of like fitting given data, like polynomial approximation and so forth, that's chapter 8 is a little easier to digest. Okay, so I'm going to make this matrix. Okay, so first I have my x and my y. I need a vector of 1s, 10 of them. Okay. And now I'll make my A. It's just I'm putting 2 columns next to each other. So all I got to do is stack them horizontally. So I use NumPy hstack to put E first and then X. So now if I look at A, so they're my 1s, and then these are all my X values. Okay. In my right-hand side, I have my Y values. So now, to solve it, all you got to do is call this function. So this is numpy.linalg. Oh, well, actually, I need to import that first. I've not imported it. I don't have it in here. Okay, import numpy.linalg as an LA. Okay, so a function is LSTSQ, least square, and you just pass the two arguments, your matrix and your right-hand side, and it will solve this problem in a least square sense. Notice there are 4 outputs. So A contains, actually, I'll call this C. That's what I called it earlier. These are my coefficients in my B and my M as an array. Residuals is really just the sum of squares of all residuals that it's actually this sum of squares that I'm trying to minimize. That is returned in this output here, so I can see how small I made it. Rank is the rank of a matrix A, which I already know is 2. And then S consists of the singular values of A. So the singular value decomposition I won't talk about now, but it's very useful for least squares problems. But for us, it's kind of a sideshow today. Okay. But it's helpful for determining accuracy of low-rank approximations and solving undetermined least squares problems as well as overdetermined, things like that. A zillion applications. And I have to say that because my advisor came up with the first general-purpose algorithm for computing it. Okay, so I solve the least squares problem. It's giving me this warning, which is not something for us to worry about. It tells you how you can suppress the warning in the future, but right now, honestly, I don't care. So now I have my output C. These are the coefficients. So this is B, the y-intercept, and then this is M, the slope. So what I want to do is I want to construct the line with these coefficients of this y-intercept and this slope. So here's what I'll do. I'll say y fit is equal to the first coefficient, which is the y-intercept, times the vector of all ones, plus the second coefficient, which is the slope, times the vector of all the x's. So now, this is my linear function evaluated all the x's. So now what I can do is, I want to do my plot again, but in addition to the data, I want to plot the line also. X and then y fit. And then I'm not going to specify a color. It's going to connect the dots and use the default color of blue. So once I do that, okay, so this is the least squares line. And since we have a lot of these points kind of clustered together in a vertical sense, that's why the line does not have much of a slope. We see that there are some outliers. So there isn't really a line that can possibly get to all of these points. But so this is the best we can do if we're using the 2 norm for minimizing. You can minimize in the sense of a different norm, like the 1 norm, but the 2 norm is easier to work with because the 2 norm is a differentiable function of the components of a vector. So you can use techniques from calculus for minimization. Whereas the 1 norm, it's kind of like the absolute value function. It's not differentiable everywhere. But L1, so the 1 norm minimization is a big thing. A lot of people are using it because it does work well. Okay. Now, if I wanted to compute the residual vector, that would be my right-hand side minus matrix vector multiplication of the matrix A and my solution C. Okay. And if I do a sum of R times R, which R times R, and you can't do this in MATLAB, you have to do r dot star. But in Python, r times r just multiplies the vectors component-wise, and then I'll sum them up, and this is what I get. Now, if I compare this to the residuals output from when I solve a least squares problem, you'll see that, except for digits displayed, they're the same value. So that's where that residual values come from. And then S, those are the two singular values of A. The smallest one is, the closer A is to a singular matrix. So in this case, it's not all that close. And then, so the columns are fairly linearly independent. And then the rank is 2. It's because as long as the x values are not all the same value, as long as it's not a constant, it's going to be linearly independent of the first column. So the rank is definitely going to be 2 in all these cases. Okay, so in general, I go back to general usage here. So these outputs, you could use numpy.linealg.least square with whatever a and right-hand side, and the first output will give you these coefficients. Now, another way, if you don't really care about all these other outputs, you just want the solution, here's what you can do. You can just say C, but because least square will return a list of the outputs, you have to put a subscript of 0 saying, whatever this returns, whatever list this sends back, I only want the first element. So then you can do that. Same warning, but those are the same values from before. Okay. But it's important to, if you look up in the documentation, what outputs does it return? Because if you're not careful, if you do something like, oh, the output I want equals this, and then you get some error because you try to do something with the output doesn't, and you find that you're interpreting the output incorrectly, check your documentation. Let's see. Where'd I put it? Oh, okay, that's convenient. Yeah, least square. So you see what it returns, these 4 items. So you can check that and make sure that everything's correct. So you can see, oh, this is what I really want, so I'll just take the first element. It's not like MATLAB where you can say, oh, I only want these things. You call this function in Python, it's returning all of them. You have to make sure to deal with it accordingly. Okay, so any questions about how we solve a least squares problem? All right. Okay, so that's one essential. Okay, so I'll just make that noted here. So we're generically switch from Ax equals B. X is equal to numpy.linealg.least square AB, and then just if X is all you want, then you get the 0 output. So other output, in order, you have R transpose R, that's residuals. Rank is a rank of A, and then S is equal to the SVD of A. In other words, like SVD in MATLAB by itself will return just the singular values, not the whole decomposition. Okay. All right, so that's least squares. So if you want to, now in the book I want to show you under iterative methods. Minimum residual method. So, okay, I'll make this note here. So minres in particular, 531 is where min-res is derived. So I won't bother with a whole derivation in this case. What I'm doing here is actually deriving GM-res for general unsymmetric matrix. And here's the algorithm. But then in a case where A is symmetric, it scales down to min-res. And I have the algorithm. Oh, I don't. Oh, that's evil of me. Okay. All right. That's strange. I thought I had it in here. Although what's really happening here is a special case of GM-res just applied to a symmetric matrix. So this is the algorithm, and the main difference, really the only difference in the algorithm, if you want to take GM-res, implement it, but use it for a case where A is symmetric and get min-res. What happens here is this loop that starts from I going from 1 to j would actually only have to go from j minus 1 to j. And that's now, actually, it's the, okay, so want to implement min-res yourself, which actually I have in mind for a default final project. Use algorithm 5.3.1 in the text, which is GM-res. But in the loop for I equals the minimum of 0 and j minus 1 up to j. So you have to make sure it's a valid index. But the point is, you have at most 2 terms in this for loop in the case of A being symmetric. Because what happens is, otherwise, because of the fact that orthogonal polynomials satisfy for a positive increasing measure, satisfy a 3-term recurrence relation, for I less than j minus 1, these coefficients, the HIJs, all end up being 0. And this matrix that's being built from all these H's, so the HJ tilde here, that is, it's normally a Hessenberg matrix for general matrix A, but in the case when A is symmetric, it is a tridiagonal matrix. The other thing is, it's not actually necessary to store all these vectors in the symmetric case. Storage is a problem because that storage increases from iteration to iteration. That's why GM-res, it's a good idea to restart it now and then to avoid having excessive storage requirements. Min-res, it's actually not necessary to do that. Okay, so all right. Now, actually, I want to check something here about if there actually is a min-res function for sparse matrices that I want to tell you about. Okay. Okay. Well, actually, I want to back up a little bit. Okay. First, we've seen this module before, SciPy sparse lin alg. Here we have all the iterative methods. And notice that, if I make it a little bigger, GM-res has an extra parameter for restart. You have to restart GM-res now and then because of the excessive storage requirements. Whereas min-res has no such parameter. It's not necessary. Okay. All right. So what happens here is, at every iteration, you're solving this this is your least squares problem, where E1 is the first column of identity. Beta naught is a quantity that's computed earlier up here. So this is your right-hand side. This is your matrix, Hj tilde, which is, in the case of asymmetric, it's tridiagonal matrix. And then Yj is your unknown. So then you, once you have this, so you solve this using like least squares, and then you take a linear combination of your vectors, and then, so that way you're able to build up your solution. Now, the way this algorithm is described, if you implement it exactly as written with the change I mentioned in the for loop, this still would have excessive storage because it is storing all of these vectors Qj. But it's possible to implement this in such a way that all this storage is not necessary. I just won't get into that right now. Okay. Now, so this is the basic idea behind MinRes, that solving this least squares problem, where this is a matrix that's almost square. It has one more row, but it does columns. So that's what makes it an overdetermined system. Okay. So this is a role that least squares plays for these kind of iterative methods, GMRes and MinRes. Okay. Now the other thing I want to discuss is partial differentiation. Suppose you have a suppose you have a 1D differentiation matrix, either forward, backward, or centered difference. So as an example, I'll use forward difference, periodic boundary conditions. So my matrix, I'll call it D1, is equal to 1 over my spacing dx. And it has minus 1s on the diagonal, and 1s on the super diagonal. Whoops. Okay, so 0, minus 1, 1, 0. Okay, so this keeps going. Okay. And things don't get interesting again until we get down to the bottom, where on the second to last row we have a minus 1 and a 1. And then, this is where periodicity comes into play. I have an extra 1 down here. And it's because we have minus 1s all down the main diagonal. Up above, we have these 1s, the super diagonal, and it wraps around to cause an additional 1 down here. So, and I'll make note this is forward difference. Okay. Now, so suppose we're given a function defined on an m by n grid. And I want to make sure I have this right for my notes. Okay. All right. And if you imagine an xy plane, so m corresponds to y values, and n corresponds to x values. And so m and n, you can think of them as a height and width of your image, for example. Okay. And I think because of time, I'll have to talk about how we work with images, like how to load images and display images, or manipulate them. Probably in a video that I'll record while I'm in London. Okay, so I'm going to let D1M refer to in the y direction. So we have using spacing dy, and then d1n equals differentiation. So, but this is still 1d. This is not partial differentiation yet in the x direction. So in other words, I'm using the appropriate spacing for each one. The matrix, everything in square brackets is the same. It's just the coefficient out front is different. Okay. So I have these set up for each one. And rows will correspond to y, because if you took matrix entries and you display them in a grid with like an xy plane, intuitively that's the convention that would make sense. So you're counting up rows along a vertical axis, and you're indexing columns along a horizontal axis. So columns correspond to x, and rows correspond to y. So how to get ddx, ddy matrices for 2D functions? It's actually simpler than you think. So use the Kronecker product. This is scipy.sparse.cron of two matrices A, B. So that's how you carry it out in Python. And it's just the cron, K-R-O-N function in MATLAB does the same thing. What does the Kronecker product do? It's easiest to describe in words. So what you do is, suppose A be, let's see, I need to make up other dimensions. P by Q, B is S by T. So just generic sizes here. Then C is equal to PS by QT. So it multiplies the row dimensions, and then that's the number of rows in the total, and then it multiplies the number of columns, and that's the total number of columns in the matrix. And what you do is, to get C, make a P by Q tiling of B. So in other words, the matrix B is repeated in a grid, a P by Q grid. Each tile is multiplied by corresponding entry of A. So I'll do an example. Okay, so import scipy.sparse as SP. And I'll make two matrices here. Okay, so like 1, 2, 3, 4. And then the other one I'll make a diagonal matrix. 5, 0, 0, 10. All right. So if I do hopefully it'll take it. Well, C is a sparse matrix, so I want to convert it to an array so I can see it. So here's what it did. It made a tiling of B. So we have 4 diagonal matrices. So it took 5, 0, 0, 10 and put it in each tile. Multiplied each tile by 1, 2, 3, 4. Now, suppose I go the other way. cron BA. So what this does is B is a diagonal matrix, so it takes 1, 2, 3, 4, tiles it, and then multiplies them by 5, 0, 0, 10. So if you look at the two of these and see the difference between them, it gives you an idea as to how the Kronecker product behaves. Okay. All right. So how does this help us with partial differentiation? If I make IM be the M by M identity and IN be the N by N identity, then it turns out partial differentiation matrices, you just need to take Kronecker products of one-dimensional differentiation matrices with the appropriate identity matrices. So then DDX, what you do is it's a Kronecker product of your 1D differentiation matrix with respect to X. Okay, I called it D1N times the M by M identity. And then partial differentiation in respect to Y, take a Kronecker product, you go the other way. It's the N by N identity, and then the M by M differentiation matrix. Under this assumption, be very careful about this, that matrices are reshaped into vectors in Fortran order, that is also MATLAB order, column by column. So in other words, if you take a matrix and you reshape it into a vector, you start with the first column, then stack it on top of the second column, third column, and so forth. And as opposed to filling it in a row by row fashion. So because what happens is, now the way this works is how you do a reshape in Python. You let U vector equal U matrix reshape, and the length of the vector is okay. So width times height, so it's M times N. So that's the length of it. And then the order is F for Fortran. But default ordering is the C convention. So C is in a C programming language, where you use two-dimensional arrays are stored in row major order rather than column major. So if you use the so be sure you reshape consistently. Either use a C order or a Fortran order. I don't really care. But if you use the C order, then this has to actually be reversed. So in C order, DDX is the Kronecker product of okay, so it's the M by M identity. Okay, so the order of these is reversed. So that's something to keep in mind there. Okay. Okay, and that's the default for Python, whereas Fortran order is the default for MATLAB. So keep it in mind if you ever have to convert MATLAB code to Python code, that there's a difference in storage. Okay, but so what I've given here, and I have to be careful about this. I've done it both ways, and this is from memory. I'm hoping I didn't mess anything up, but certainly there's a reversal here because of the different orderings. So I may have to try this later and make sure. Okay. So that's how you make these differentiation matrices. They do like sp dot cron. Okay, and the reason why is when you are storing in column major order, that means that neighboring points in your vector correspond to generally neighboring y values. So what's happening here in a DDY case, it's keeping nearby entries in this single variable differentiation matrix is keeping them together and multiplying them by 1 or 0 into different tiles. Whereas in the case of differentiation with respect to x, neighboring points of neighboring x values are spaced m apart. So that's why we have these m by m identity matrices, and then those are tiled and multiplied by the appropriate entries of this matrix. Okay. So this is how you construct these partial differentiation matrices. And what I've done is I've shown it here for the forward difference, but you can do the same thing for like the backward difference and center difference. You use a Kronecker product in exactly the same way. Now, the thing is, the forward and backward difference are first order accurate. Center difference is second order accurate. So you might think, well, why would I ever use a forward and backward difference? But keep in mind the second derivative center difference can actually be written as a product of forward and backward difference. So if you use both of them together, you multiply those matrices, you get the center difference. Whereas if you took the center difference and you squared it, you'd be using every other point in your grid. So that actually ends up being less accurate than this option. You want to use the points nearby. So that's why forward backward difference are still useful. And for PDE of a form like du dt is equal to derivative with respect to x coefficient du dx plus d dy g du dy. One thing you can do, there are many ways to discretize this, and in that I'll send up the latest version of a textbook to you where exercise 10 in chapter 14 deals with this kind of expression and shows you different ways to discretize in space. You have it's customary to use one way is you would use different differentiation rules for this derivative versus this one. For instance, you could use like forward difference here and backward difference here, or vice versa. And that exercise shows another way that uses a staggered grid, because you would not use both forward difference here and here, or both backward difference. The reason why is sure that the resulting matrix that you get is symmetric. So if you use like forward here and backward here, or vice versa, that will because the matrices for forward and backward difference are negative transposes of each other. So by using one here and the other one here, that guarantees the matrix is symmetric. So in that exercise, there's also an approach using a staggered grid of a coefficient that also gives you a symmetric matrix. It might actually be a better choice all the way around. And symmetry is important because if you're solving system linear equations involving a matrix like this, these methods use half a number of floating point operations generally in a symmetric case. So that's certainly significant. Okay. So So these are certain ingredients. I haven't got to a point yet where I can actually describe what I want you to do assignment-wise, but I've covered a lot of what's needed, um, and I'll prepare something to hopefully either later this week or if not, because I'm traveling for the next couple of days, but certainly early early next week. Okay. Now, I do need to end soon, but I want to know if anybody has any questions about either of the assignments. I haven't gotten I got most people's assignment 1. Only one person's assignment 2. So does anyone have any questions? The 3 of you here have any questions about that? Yeah. Yeah. Well, then you only take that part of a column and pass only that part to argmax. But then that index will be thrown off because then you have to take that index and make it an index within the whole column. So you have to shift it. Oh wait, you look at we need to start from a diagonal down. Yeah. So you're not gonna start at 0. Okay. Yeah. Now the thing is here there's no shifting needed because you're starting from the top, so you're not seeing the same effect. Um, like okay, so for example, for the third column, you have 0, 4, 3, 7. So that is so it's going to pick an argmax return 3 because it's the 4th element. But that is the element of index 5 within the whole column. So so you have to shift by 2. Now, how much do you have to shift by in general? See what happens if this happens in the second column versus the 4th column or something like that. How much do you have to shift? Because how much you shift depends on how many entries you are leaving out. Yeah. Alrighty. Okay. Any other questions? Yeah. Oh, okay. Well, in Python, it's not a tick function. I called the variable tick, but it's really the time function. Yeah. So in other words, what I did was, if you look back at my script, I saved the current time in a variable that I called tick, and then I performed my computation. Then afterwards, call time again and save that in talk, and then I subtracted off tick, and that gave me the total amount of time that had passed. Yeah, so it's really the time function is the only one you're really using, and you can save that. So if you, as long as you call time both before and after your computation and save them in whatever variables, then the difference of those two variables will give you the amount of time that has passed. But you got to do it all in one command, so that you're not taking into account your typing speed. So something like I'll do the operation I just did. And then like that. Oh, I have to import something.
I think I'm talking about take as in
Take!
Yeah.
It totally sounded like tick. Okay, hold on a second. I need to check something though, because now, unfortunately, I've just typed something wrong. Okay. Okay. Oh, dang it. Oh, time. Okay, sorry. I'm gonna do this last command correctly, and then I'll answer your question. Okay. Okay. So that's how many seconds the Chronicle product took. Okay. Now take. So dang it. Okay. Oh. So for instance, okay, I'll show you an example. I'm gonna make a. Well, actually, I already have a. Okay, so I have this array here. So what I want to do is x.take, and I pass some indices. Now my indices is a 10-element vector, so I can use any indices between 0 and 9. So for example, this takes the first element, last element, second element. This is how I can pass whatever valid indices I want in whatever order. Now, what you're doing in your Gauss elimination code is you're representing P initially as a vector of the indices 0 through n minus 1. And you keep scrambling them as you do row interchanges. So you can do b.take P, and that will select the entries of B in the proper order. Okay. Any other questions?
Concerning the solve A as B, A is equal to B.
Yeah.
We are supposed to. Are we supposed to use just forward and backwards?
Well, you use Gauss elimination first to get L and U, and then forward substitution and back substitution. Yeah. So, but yeah, it's just those 3 tasks. Yeah, not much. Any other questions? Okay, well, then we're calling it a day. I'll try to get all this stuff up. I may not be able to get it up as fast as I usually do because I'm traveling, but I will get it up on YouTube and also on the site as soon as possible.